Okay, so we're going to go ahead and continue on with Unit 3, which is about the normal curve. What you want to do with these set of notes, you want to put it right behind Chapter 5, okay? So we're taking a look at some free response questions that actually come from past AP tests. So this first one that we're going to look at comes from the 2011 AP Stats free response section, so I'll just put that on there. And it is actually number 1. Okay, so just reading the initial information. A professional sports team evaluates potential players for a certain position based on 2 main characteristics, speed and strength. Speed is measured by the time required to run a distance of 40 yards, with smaller times indicating more desirable, faster speeds. From previous speed data for all players in this position, the times to run 40 yards have a mean of 4.6 seconds and a standard deviation of 0.15 seconds with a minimum time of 4.4 seconds as shown in the table below. Okay, so here's our mean, standard deviation, and our minimum. The question, based on the relationship between the mean, standard deviation, and minimum time, is it reasonable to believe that the distribution of 40-yard running times is approximately normal? Explain. Okay, now reading this question, we can see that there are 2 things we need to answer. Is it reasonable? So that's a yes or no question, and then we want to be able to justify. Now also, just looking at the question, it says based on the relationship between the mean, standard deviation, and the minimum time, right? We see that it has to be based off of that. That means that we have to mention all 3 of the things for us to be able to actually get the full credit, right? That's clear in the question itself, okay? So is it approximately normal? Now we know that if you have approximately normal data, it's going to look symmetric, right? So I'm going to go ahead and sketch out what a normal model should look like to us, right? So to us, it's going to look symmetric, and the mean is going to be in the very middle. Okay, the mean is 4.6, so I'll go ahead and put that in. And then when we draw this model, we always add 3 standard deviations above. So 1, 2, 3, and then below 1, 2, 3. Now our standard deviation is 0.15, so I'm going to add 0.15 to 4.6, and then I'm going to get 4.75, and then we have 4.9, and then we have 5.05, and then below we are going to get 4.45, 4.3, and 4.15. Okay, so thinking about our normal curve, we know that 68% of the data needs to be within 1 standard deviation, right? So that's our empirical rule. And then we know that 95% needs to be within 2 standard deviation, and then 99.7% needs to be within 3 standard deviations. Okay, now if that's true, then we could say that it's normal. Alright, so we have used the mean and standard deviation to draw the picture. Let's go ahead and take a look at the minimum. So 4.4 seconds. Now based off this model, 4.4 seconds is going to be right around over here. Okay. Now, if I were to find the area below 4.4 seconds, this area, that's the percentage of the data that should be there. Okay. Now the thing is, 4.4 is our smallest, fastest time. So then that's telling us that this can't fit into a normal model. Okay. Because if I actually calculated the z-score for 4.4 seconds, so z is equal to 4.4 minus the mean, which is 4.6 over your standard deviation, which is 0.15, right? We get a z-score of negative 1.33. When I go to my table and I look for that z-score to find the area that is underneath, right? So that's going to be the probability that a time is less than 4.4 seconds. We're going to see that we get 0.092, which is going to be about 9.2%. Okay, so 9.2%. So what the normal model tells us is that this time, 4.4 seconds, it needs to have 9.2% of data below it, but if you're looking, there isn't any. That's the smallest time, right? That's the smallest number that we have, and so that tells us that no, this is not reasonably distributed. And so I'm going to go ahead and formally write down that thinking so that we can ultimately answer the question. So it's a first of all yes or no question, so I'm going to put no, and then I'm going to just straight out copy this part of the question so I know I'm completely answering it, okay? So no, it is not reasonable to believe, right, that the distribution of 40-yard running times is approximately normal. Okay, so no, it is not reasonable to believe that the distribution of 40-yard running times is approximately normal. Now let us give them a little bit more information. So we know that the minimum time of 4.4 seconds is only 1.33 standard deviations below the mean. Alright, and then when we looked at our table to find the area below that 1.33 standard deviations, right, we saw that it should be 9.2%. So in a normal distribution, 9.2% of the data should be below the 4.4 seconds time, but there is no data. Okay, and at that point we have fully justified why this cannot be approximately normal. Okay, let's go ahead and move on to part B. Strength is measured by the amount of weight lifted, with more weight indicating more desirable, greater strength. From previous strength data for all players in this position, the amount of weight lifted has a mean of 310 pounds and a standard deviation of 25 pounds as shown in the table below. Okay, so we have mean and we have standard deviation. So mu for mean and then sigma for standard deviation. We want to go ahead and calculate the z-score for the player in this position who can actually lift the weight of 370 pounds. Okay, so here is my z-score formula. Z is equal to an observation minus the mean over the standard deviation. Okay, and this is our observation right here. Okay, so that's our parameter that we're interested in finding the z-score for. So I'm going to go ahead and substitute my information to calculate the z-score. So z is equal to 370 minus the mean, which is 310, over our standard deviation, which is 25 pounds. Now when you punch that into the calculator, you will have 2.4. So we are 2.4 standard deviations above the mean. Okay, so that's the first part we calculated. Now we have to interpret. Okay, so what is happening is this particular player, right, can lift a weight that is 2.4 standard deviations above the mean for all the previous players in this particular position. Okay, so let's go ahead and write that down. The amount of weight this player can can lift is more, or is rather 2.4 standard deviations above the mean amount of weight lifted by past players in this position. Okay, so I'm making sure that I fully give context. I'm not just going to say that it is going to be 2.4 standard deviations above the mean. I'm going to say the mean amount of weight lifted by past players in this position. So I actually want to define what that mean is, just in case, because I want to make sure that I can show the AP reader that I can fully interpret what the z-score means in the context of that problem. Okay, so there's part B. Part C, the characteristics of speed and strength are considered to be of equal importance to the team in selecting a player for the position. Based on the information about the means and standard deviations of the speed and strength data for all players and the measurements listed in the table below for players A and B, which player should this team select if the team can only select one of the two players? We must justify our answer. Okay, so there are two questions in it. Are we choosing player A or B? And why should we choose player A or B? Okay, now, if I'm looking just at their times, right? So the mean time was 4.6 seconds for the running, the time to run the 40 yards, and both of these are under, and then it looks like player A is faster than player B. Okay, so they're both under, but player A looks faster. Now if I'm looking at the amount of weight lifted, again, the mean from above was 310 pounds. So player A is lifting 370 pounds versus player B 375 pounds. And so if we're watching at what's happening here, it's clear that player B is stronger. Okay, so we see that player A is faster, player B is stronger, and those are weighted equally to us. So we have to figure out a way to be able to compare this so that we can consider what the mean of this and then the mean of that. And the best way to do that is actually by calculating the z-score so that we have a better idea on where their time is relative to the mean and where their weight lifted is relative to the mean. And so I'm going to go ahead and calculate those z-scores. So the 40-yard running times is what I'll put on this side. Okay, so we have player A, so I'm just going to put A right here. So this is player A. So player A has a running time of 4.42 seconds, so 4.42, and the mean again was 4.6. Again, I'm getting that information from above. And our standard deviation of running times was 0.15 seconds. And then what we have is negative 1.2. Okay. Now for player B, right, so I'm going to calculate player B's z-score. So their running time was 4.57 seconds. And the mean was 4.6 over 0.15. Okay, and then we have negative 0.2. Alright, so again, A is faster than B. In fact, A is faster than B by one whole standard deviation, right? It's one extra standard deviation away from the mean. Okay, so that's just giving us a general idea of where A is relative to the average. So on this side, let's look at weight, and then let's go ahead and decide which player we want to choose. So weight lifted. Okay, I have to calculate that for player A. So z-score is equal to, so player A is lifting 370, the mean is 310, our standard deviation is 25. When we put that in the calculator, we're going to get a standard deviation of 2.4. For player B, right? So we have our z-score formula, right? So player B lifts 375 pounds, and the mean is 310, and then our standard deviation is 25. Punch that into the calculator, you're going to get 2.6. Okay, so we already knew that player B was going to be lifting more, right, than player A, but now just looking at this, we see that he's only lifting 0.2 standard deviations more, right, which isn't as big of a difference as player A's running time, right? He's running one whole standard deviation bigger, and at that point, I am actually going to argue that we should vote for player A to join the team. So yes, he's not as strong, right? But he's only slightly less strong. He's like much more faster based off these standard deviations. Okay, so I'm going to go ahead and write out formally what my argument is. Okay, so both player A and B are faster, right? We established that. Then average based on their z-scores, right? And we know that's true because they're both negative. Okay, so their z-scores of negative 1.2 and negative 0.2. And we know that both lift weight above average based on their z-scores of 2.4 and 2.6. And then I'm just going to add respectively so that they know that they're reading that negative 1.2 belongs to A and 2.4 belongs to A. And then for B, we have a standard deviation of negative 0.2 and of 2.6. Okay, so just giving them my information that I had calculated, right? So we calculated it for a reason, so I want to make them aware of it. And then I'm going to go ahead and start making my argument that A is the better player. Okay, so while player B is able to lift more, than player A, and we know this because player B's z-score is higher by 0.2. Their running times have a larger difference and then that difference, right, remember when we were looking at this, was one standard deviation,